Hello, everyone. Could you hear me?
I can hear you.
Okay, yeah, thank you. So today, let's quickly review what we have talking about last week. Okay, so this part we talk about array in a struct and a union. Talk a little bit. In the for the array, we particularly talk about how to geolocate the ith element. So take an example. If we have the char, we first figure out the starting address of it should be XA. And if we want to geolocate the, let's see, the element indexed by 3. We want to find its location. And first of all, we figure out each element have size 1 byte. And if you look at A0, it is the address of it is XA. If you look at A1, it's going to be XA plus 1. A2, it will be XA plus 2. Okay. So if we want to look at A3, the address of it should be XA plus 3. And we can generalize the case. If you look at AI, and you want to look at its address, it's going to be XA plus I. There is a case for the A. We also talk about the case for B. For the things could be would be different because each element right now is 8 bytes. So we can talk about here. If we write the first element would be B0, second one would be B2, B1, and the B2, and each element, because it's a chart pointer, it's an address, so it is 8 bytes. We also have the starting address as XB. Because each element right now is 8 bytes, if we want to look at the address for B1, we no longer plus 1, but plus 8. Do you know the reason? Because each byte have each unique address. So B0 would occupy XB, 1 byte, XB plus 1, the second byte, XB plus 2, the third byte, so on and so on. We have 8 bytes. So we would, starting from XB to XB plus 7, this 8 bytes would hold B0. And XB plus 8 starts the next B1. That's the reason we plus 8. And we can apply the same rule. If we look at a B2, we would have XB plus 8 plus 8. So we need plus 2 8s. So we can generalize the case. If we look at BI, and we have the starting address as XB, then we would have the index I times the size of each element, which is 8. So this would be the equation to get the address for BI. This is what we talk about how to geolocate one element in the array. Okay. We also talk about the pointer arithmetic. For the pointer arithmetic, we have the integer E10, and we look at the expression E. If we write down expression in C, that will be an integer pointer. here, if you have the EI, that is looking one element, then the type of it is integer. If we look at E2 and then extract the address, then it will be integer pointer, and it's xe plus 8. If we do arithmetic over the pointer, what we really do is we want to we actually calculate the value with a scalar. So if we have the xe, we talked about this is the starting address for the array. And then if we calculate the address, we need to do a scalar because the integer is a type. We need a scalar 4 so that we can get the correct address of it. So if you do arithmetic plus I minus 1, we are looking at the address of E I minus 1. And also we talked about if we do have 2 pointers, we want to minus them. You can think about this E is the address for E0. So if EI is the address minus E0 its address, we are having I minus 0 directly. Okay. So far, do you have any questions? Okay. We also talk about how to do a reverse engineering over this script. And in this example, you can see we have A0 initialize that value to be 1, A4 initialize that value to be 10. We look at the assembly code right here, so we can figure out RBP minus 48 should be the place holding A0, and the RBP minus 32 would be placed to hold A4. And so that we can come up with an equation to do that. We want to look at the address of A4. We want to look at it. So what we can do using the equation is have the start address AX, XA, plus the index, which is 4, and the integer, we don't know what is the type of it. So we just put down S to denote the size of each element. This equation is what we talked about. Now we can do the calculation. We already know the place to hold A4 is RBP minus 32. And XA, which is starting address of the array, so that would be RBP minus 48. And we plus 4 times S. So if we do the calculation right here, we can get RBP off and move the 48 to the left side. So we can have 16 at the left side, and the right side is 4 times S. So we can know that S should be 4. We figure out the size for each element is 4, and that should be an integer as a result. This is the reverse engineering part. And also here we talk about the nested arrays. For the nested array, we talk about the we use one-dimensional memory to store two-dimensional matrix. And in such a case, we would do as follows. Let's say we have a matrix like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the matrix. If we want to store it in the memory, we're looking at the first row and put that first row into the memory. We will put down 1, 2, 3, and then we would do 4, 5, 6, 4, 5, 6, and then we do the next one, 7, 8, 9, so on and so on. And that's the way we store a matrix in our array, so in our memory. And that's how to do that. In this example, we have the A53. We have 5 rows, 3 columns. And you can see here, the first one we put down in the memory is A00, then A01, A02. This is the first subarray. And we use A0 to denote the subarray. And then we can go to second subarray, which is doing A10, A11, A12. This is second subarray. A2 is the third subarray, so on and so on. If we want to look at the address of a particular item, let's look at A12. And we talk about the ways we make the calculation. First of all, XA denotes the starting address of this array. And then right now, let's talk about the equation. We can get the address of it. First of all, we need to find out where is the A1. Here's the A1. We want to find its address. The way we can find its address is to count how many subarrays in front. We have one subarray in front, and this subarray have 3 elements. Each element is integer, which is 4 bytes. So by plus this number, we would get to the A1. We find the subarray. So the blue part is trying to find the subarray. As long as you find a subarray, you want to do the offset within this subarray to find the index 2. So we will put down 2 and multiply the size of the element, which is 4. So if you do the calculation altogether, you can find the address for A12. That is XA plus 12 plus 8. That is how we get XA plus 20. So in short, we have the blue part to find out where is A1. And then we have the pink part to find the index by 2. That's how we do the calculation. We also talk about the reverse engineering problem here. And let's quickly go through it. It's still the similar question. We want to find out the type of this nested array. So we look at A00, and we make that to be 1. So we look at move number 1 to RBP minus 208. So RBP minus 208, that is place holding A00. And also we can find the second line, which is move 10 to the place. The place right now is RBP minus 1 to 2. So we can know that this place is having A43. And we use a similar equation right now. We want to calculate A43. What is the address of it? We talk about the general rule to do the calculation. So first of all, we find the starting address of the array, and then we are trying to find out where is A4, the subarray A4. The way we find out is we use the index 4. That means we have 4 subarrays in front, and then we times how many elements in each subarray. We have 10. That is column number. And for each one, we don't know the size, so we put down S. This 4 times 10 times S would find A4. After we find A4, we want the offset to find the element indexed by 3. So we put down 3 here and S right here. And we can still do the similar trick. We already know what is the address for A43. A43 is RBP, let's see, RBP minus 122. XA, which is starting address of this array, is also the address for A00. So we can know that RBP minus 208 would be XA, and then we plus 43S. If we do the calculation right here, move 208 to the left side, then we would have 86 at the left side, and the right side is 43. So then we have S equal to 2. That is how we find short. And now, before we start our new material, this is a pop quiz exercise. You need to email to me. Here we specify a double B10, 12. We have 10 elements, 10 rows. We have 12 columns. And the starting address of it is XB. Our question right now is, what is data type for B3? And what is the value for B3? And the second question is, what is data type for B36? And what is the address of it? So I will give you 5 minutes. You can work on these questions. This is pop quiz. Please email me your answers. We test for the attendance. So whatever you send me, you will receive full score. So I'll give you 5 minutes to do that. A question from Manson. When does this need to be emailed by? It's the end of today's class. My email address, I will type into the chat window. It's basically sli@uccs.edu. A question from Tyler. Does we only have 5 minutes to get this email to you? You have more minutes. As long as you send me before the end of today's class, that's fine. So this exercise is quite important for our class. It tests the idea when you have a piece of memory, you have certain items inside of it, how we can geolocate any of them. And that is helpful when we read the assembly code.
Can you post your email in the chat?
He did.
Never mind, I saw it.
Okay, I received 4 submissions so far, so I will give you more time to work on that. Okay. So continue to make the submissions. Now I will explain how to solve this problem. So many of you send me the answers. Let's see whether you get the right answer. Okay, so first of all, we see um, this nest array. We have 10 rows and 12 um, columns. Now, our first question is, what is the data type for B3? For this part, uh, we would go from B at first. Let's see, we have the B, and the data type of it is double pointer to pointer. So if we only write down B, it should be a pointer to pointer and of double. If you write down BI, in this case we have B3, the type of it is double pointer. And if we have Bij, and this time we would have a double. We're looking the elements indexed by I and j, row I and the column j, so it should be a double. You can see here, as long as we have one bracket, and then we would reduce one pointer. If we have double brackets, we reduce both pointers to be double. And this is quite a rule if we have nested array. So B3 would be double pointer. And now let's look at what is the value. For this question, I would draw the memory space. Let's see, it's starting from XB. This is XB. And now let's draw first part, which is having which is a subarray. We would denote this part to be B0. This is the first subarray, and in this red box, you would have B01. No, sorry. You would have the B00, B01, B02, B03 until B011. This is the first row. I'll draw here. We have 10 row, 12 column. This is the first row of the matrix. We put that row into here. That is the B0. We'll use this red box to denote it. We need a B3, so we need to put down another box. The second box. This is the next subarray. We will put down B1. We can continue this process. Next one, we're gonna be B2, and the last one is what we need. That is B3. We want the address of it, the B3. That's the starting address of B3. So we can do the calculation. If you want to do the calculation, one thing we need to look at is for the first box, B0. We need to do the calculation how many elements it has. You can look at the example here. We gotta have 12 elements for B0. Right? So we have 12 elements, and each element is double, which is 8 bytes. So for each box, you would have 12 times 8 bytes. Is there any questions? And you can see here how many such subarray boxes we have. The red, blue, pink, we have 3. So you can write down here that is another 12 times 8, the pink 12 times 8. So you can see here we have this many bytes in between. So if we want to look at the starting address for B3, it would be XB plus 12 times 8. This is the size for each subarray. How many subarray we have? We have 3. So we calculate them together, you would get the address for B3 or B3. It would be XB plus, let's see, what is this number? 12 times 8. So we would plus 288. That is, that will be the value for B3. Any questions? Okay. So that's how we get the B3. Now we look at a B36. We just draw it here. Let's have this black one. Let's just move this black one here. We already know that this black one, the starting address of it is XB plus 288. Now we want to look at the 6. So what we can do, we can draw it. First one gonna be B30. Next one B31. We want to look at B36. If you want to do that, you can see it's pretty similar with the array case, the I times the size, right? If we do that, the B31, we should have XB plus 288 plus 8, right? So that we can point to the B31. And if we look at a B32, we need an XB plus 288 plus 8 times 2. So 2 here is a 2 here. If we do the calculation, we would find if we put down 6 here, if you put down 6 here, what we're gonna do is we would plus 6 times 8 plus 6 times 8, and the result's gonna be XB. Let me do the calculation here. It will be 336. That will be the answer. Great. A question from Nick. I didn't understand you were looking for the address value. I thought you meant the value stored there. Do you mean the B3 or B36? Ah, I see. Yeah, Nick, that's a good question. So if we look at what is content for B3 or the value stored in B3, I see your question. So B3 is a double pointer. It's gonna be an address. So if we understand, try to understand this, we should put the address xb plus 288 in B3. So B3 is different from B3 0. B3 means a double pointer, which is the address for the subarray B3. B3 0 would be the first element in B3 subarray. That's a good question, Nick. Is there any other questions? Okay. So this exercise is important. If you still have questions, please come to my office hours or read textbooks. And it will probably go into our final exam. A question from Tyler. This is only pop quiz, correct? Yes. This, as far as I remember, this should be our first pop quiz. We will have more during the semester. Okay. Now let's look at the struct. Last time we talked about the struct. There's no mathematical way to do the calculation, geolocate any of the elements. We need to go one by one in order to find its address. So we talked about, if we look at the A1, this guy, if we look at its address, this is the way we get its address. What we're gonna do is we just count. This first one is 4 bytes. So second J is 4 bytes. And the first A0, that is integer also, is also 4 bytes. So the starting address of the A1 gonna be 12. So that's how we get the address for A1. Also, we give you an example. This example is to do a linked list, try to do a summation over each node. The right side is assembly code doing the job. And also we talk about union. The union, the declaration of the union is very similar with struct. The only difference is the keyword union versus struct. And inside of it, if we make the example the same, we would find that in the memory, in our computer memory, they are handled differently. For the struct, there's 3 kinds of variables. We place them in our memory at the same time. But for the union, we only interpret the same space to be the char in our example, or the integer array, or the double. And the size of the union is determined by the largest data type. So char C is 1 byte, integer array is 8 bytes, double is 8 bytes. So we would choose 8 bytes to be the size of the union. And this 8 bytes either interpreted as a char, and this, or it could be interpreted as an integer array, or it could be interpreted as a double, but not all at the same time. We can only interpret 8 bytes to be one of them each time. That's the difference from union. And we talk about why we need union. Let's see, we have data structure like this. We have nodes, but the nodes, they are different. Some nodes, like the nodes here, they have the child, right? We have the pointer, left pointer, right pointer, that is pointing to the left node, child node, or the right child node. Okay, so some nodes like 2 or 6, we have children. We need 2 pointers pointing to the left child and the right child. Some nodes like 16, 18, 21, these nodes, they are children. They have parents for sure, but they don't have offspring. So for these nodes, 16, 18, 21, they're different from the previous nodes. Let's see, if we use the data structure like this, we only use 16. We only use 16 to store data. No, we only use a node which is don't have the offspring to store data. And if the node is having children, we usually don't have data in it. Then we, if we want to implement a data structure like this, things could be very different. Let's see, we implement the nodes by struct. We put down struct right here. If we implement, you can see here the struct have 2 pointers. Each pointer is 8 bytes. And also we have the data array, which is 8 bytes because it's double times 2. We have 16 bytes for the 16 bytes for the data part. So if we use this node as this struct to implement node 2, you would find that we need 32 bytes for node 2. And for these 32 bytes, you would find we only need the left pointer, right pointer, and the data part. We don't need that part, but it occupies space. So we need 32 bytes to store node 2. And similarly, if we look at node 16, we still need 32 bytes. Sorry. So if we look at the 16, we still need 32 bytes. Let me change the color. To denote it. For this 16, we don't need the left and the right pointers, but we need the data. So we just occupy the data, have the left and right to be wasted. So if we use a struct to implement this data structure, we only use, no matter it is nodes like number 2 or nodes like number 16, we only use half of the space. We will waste half of the space because of this feature. What we can do? We can use union. Here we define the union. We can define in the union, we have the struct. This struct is trying to define the left and the right pointers, or we can interpret the same space as a data. So if you look at the size of the union, it is the bigger. If you look at a struct, that is 16 bytes. If you look at the double array, it is 16 bytes as well. So the size of our union would be 16 bytes. In previously, the size of the struct is 32 bytes, right? Here, it is 16 bytes. So if we look at node number 2, if we use that to implement, use the union to implement node number 2, you can see that we would interpret the 16 bytes to be the first case, the left and the right pointers. And if we want to use the same structure to implement 16, this time we would use the 16 bytes and interpret that to be the double array. So you can see here, if we use the union data structure to implement the same data structure, we would have no waste of space. We save a lot of space. Here comes one slight problem. When we feed a node, either 2 or 16, we feed the node to a function. And this node, we wanted this function to work upon this node. And this function, we have no way to tell whether this node should be interpreted to be the pointers or interpreted as double array. So we need a little bit of help from that. What we do is we would define the type part. This type is tell whether we're interpreting the node to be the pointers, or we interpret the space to be the data. This type is trying to tell us, and this type should appear in every node. So that you can see here, we come up with a struct, and this struct would have the first part as a type, the second part is a union. Again, in this union, we have two possible choices, either pointers or data array. So this union would be 16 bytes. And the type part is 4 bytes. So if we use this one, it denotes a node, we would need 20 bytes. And this 20 bytes includes the type information. That means if you feed this node to a function, the function can check the type part and decide whether it should be interpreted as pointers or interpreted as data. So that's a good thing about union. Do you have any questions about the union and the struct, and what's the difference of them, and why union sometimes we prefer to use? Okay, let's look at the next part. Next part, we would explain why we see blank space over here. We define struct, we see the blank space, we will explain why we have them. That is called data alignment. Here is a data alignment example. So in the main function, we declare a struct. The first one, integer, C is char, J is the integer again. Then we want to initialize the I to be 10. So we see here, RBP minus 12. So if we draw something right here, let's see, here is the RBP. This is a stack. Here's the RBP. Again, each slot is 8 bytes. Okay, if we do RBP minus 12, we put 10 inside of it. We can, left side is smaller, so RBP minus 12. Okay, I need to redraw a little bit. Let's see, here is RBP. Now we look at RBP minus 12. We need a we go to here. Here should be RBP minus 12. And we move 10 inside of it. So we're gonna put 10 over here. That is RBP minus 12. Here is RBP minus 12. And we put 10 inside of it. And we also have RBP minus 8. We put down 1 in it. So if we do that, RBP minus 8, there will be it. We put character 1 inside of it. We also have RBP minus 4. We put 20 in it. There is RBP minus 4. We put down 20. So if we look at this example, you would find that in between, we have the space to be empty. Here is a live example why the phenomenon that in the space we have some places to be empty. And let me show you why. This is called data alignment. And for data alignment, this is what the CPU hardware prefers to do. That is for any primitive object of bytes, k bytes. That is the size. Let's see, this object right now is the green part in our example, green part. And this green part, this is the object or variable, and the size of it is k bytes. If the green is integer, and we would have 4 bytes, right? You can think about this green part as an integer, if you like. And what we hope to have is the address is a multiple of k. So the starting address of this object should be the multiple of k. That means when we store one variable or object in our memory, we have preference about the starting address. The starting address is gonna be the multiple of k. That's the reason we sometimes have empty in the memory. let's look at this example. So the first one, the yellow part is a char. It's a 1 byte. For 1 byte, if we look at its address, which is 2, 2 is a multiple of 1, right? So for char, you can put down in any of the slots you like, because any address is a multiple of 1. So char naturally satisfies the data alignment requirements. The second example is a short. Short is 2 bytes. For these 2 bytes, you need to find the starting address to be the multiple of 2. So 0 can be the starting address, 4 can be the starting address, but not 7, not 9, because they are not the multiple of 2. So a short variable cannot have a starting address like 7 or 9, because 7 and 9 is not a multiple of 2. And the last example is integer. Integer we talk about that is 4 bytes. And if we look at the starting address, 0 definitely satisfying it's a multiple of it. 4 can be, 8 is eligible, but not 2, not 3, not 5, not 6. So you cannot start an integer at the address 2, 3, 5, 6 number like that. You have to start with 0 for 8. That's a data alignment requirement. And some of you may wonder why we have these requirements. The reason is because of the architecture design. If we want to having such a data alignment requirements, it will make the CPU easier to fetch the data from our memory. Yeah, that's because of the CPU design. And now let me check the chat window. A question from Sherman from the previous example. How is -4 come after -8? So if we look at -4 come after with -8, the reason, let me see, -8, okay, J. It is okay, I see the reason. So for the assembly, you can switch the 2 lines if you like. That doesn't matter if you first move 20 to -4, and then move number 49 to -8. That's fine. I believe the one important observation is if we look at I in the struct, I is having smaller address. We put down I far away from the base pointer. That is 10, right? I's value is 10. We put further away from the base pointer. Why do we have such an order? Because for the struct, the I is having the smaller address than C. C is having smaller address than J. So I should have the smallest address. In this example, smallest address is RBP -12. Okay, that's why RBP -12 should come with I. It is still the same concept we talk about variables. Struct is very special variable. You can regard it to be. And as a we would use a smaller address
to store I, and then that's the order it adopts. And this is what it would appear on our stack. Okay. Is there any other questions?
You might have answered it. I think I might have just worded my question a bit wrong too. My question was, it just when I was thinking about it before you wrote it down in your memory, I was thinking that 20 should be in the line that RBP points at, because -8 is the start of the next line. So wouldn't -4 still be in the first line that RBP points at, or is that not the case?
Sorry, could you say again?
So I was thinking because -4 is only 4 bits, it would still be in the first byte that RBP points at. So it would be in the first line that RBP points at. Basically, I thought 20 would be up above where it is by one line.
Okay, I see.
Is that not the case?
Not
And
the
if so, why?
Yeah, let me show you. The RBP is the address of this subslot. Do you remember the one slot is 8 bytes in our assumption? We have 8 subslots to divide it. And 1, 2, 3, 4, 5, 6, 7, 8. Okay. And the RBP is pointing to the leftmost one, also the smallest address in these 8 subslots. And if we -4, we're coming to here. Here is RBP -4. 1, 2, 3, 4. Let me make it more clear.
I think I see.
Oh yeah,
that makes sense.
Yeah, great. Can you change to here? Yeah. So if we RBP -4, we would come to here, and then we need a store 20. So we need extra 3 subslots to contain 20. So 20 appears here. Yeah, that's a good question. Is there any other questions? Okay, let's look at some exercise. So in this exercise, we have the struct S1. We have the integer I, char C, integer J. My question, does this memory layout satisfy the data alignment requirement? Yes or no? Okay, good. So this memory layout doesn't satisfy the data alignment. Let's look at the first one, which is integer I. For the integer I, we have 4 bytes. 0 could be a good starting address for it. And let's look at char. Char is right here. Because char can be at any places. It's just 1 byte. Any places is multiple of 1. So that doesn't matter. If we look at J, J has some problem. The 5, the starting address 5 is not a multiple of 4. So J doesn't satisfy the data alignment requirement. And here is how we satisfy it. First of all, I, we don't need to change. C, don't need to change. J, we would we would delay j into the address 8, which is a multiple of 4. So we would insert 3 gray areas, basically leave it blank. These 3 areas, we would leave it blank. This is why we would have blank space in the struct, because we want to make sure j starts with a multiple of 4. So the smallest one is 8. So we need to have 5, 6, 7 to be empty. So that's why we see blank spaces in between. Okay. Here's another example. For this one, we have first we have I and J and have C. Now the question is, does this satisfy the data alignment as well? So for this one, if we look at the first I, starting address is 0, and then J would be starting with 4, char with 8. Seems like everything looks good, but the answer is it doesn't satisfy the data alignment. Let's look at the reason. So if we look at this structure, there could be a chance that we would start an array of this structure. So if you look at if we create an array var, which is a struct s2 type, and the first item doesn't matter. But if we look at the second item, if we put down var 1, that's a problem. So from here, 9, 10, 11, 12, we would put down the integer I here, and a 9 is not a multiple of 4, so it will not work if we start an array. So we still need this extra 3 blank space to make sure if we start var 1, our new integer I would start with multiple of 4 as well. So the right side of this memory layout would be work even if we create a array of the struct. So we still need 3 extra blank space because our struct could be used as array, and we want to make sure every element in the array is also satisfying the data alignment. Okay. Is there any questions? Why this guy is not satisfying? Okay. Okay, if you don't have questions, let's have 10 minutes break. We will be back at 3:05, and we will continue to do 2 exercises here. Yeah, see you later at 3:05.
Okay, let's continue. Now we have two exercises. So we want to calculate what is the size for each of them. Sorry. Okay. So the first one, we have a struct. For this struct, we first start with the integer, and then we give a char. Then we start a union. And in the second example, we start from integer, char, we start from the struct. Now we know that the memory layout of these two structures, they should satisfy the data alignment requirements. I will give you 6 minutes. You can try to figure out what is the size for each struct, or in other words, did we insert some blank space in between to satisfy data alignment? And what is the size for each of them? Okay, let's first start from the first one. That's one by one. First one, let's see what is the size for the first struct. I will give you 4 minutes. You can put in the chat window what is the size for it.
Okay, let's look at the first one. What is size for it? Let's draw the memory like this. So we still assume starting from address 0. So we need a, oh, there's so many to draw. Let's see. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So first of all, we need to put an integer in it. So we would use 0 to 3 to put down integer a. And then we would use the char b, the next one, to put down char b. And now we need to put down union again. For the union, we have two possible choices. Either we have 4 bytes integer or 1 byte char. So we would choose union space should be 4. Okay, so we can start union right here, but which is not okay because the address right after B would be 5. 5 is not a multiple of 4, so we have to postpone the union. So we cannot put union here. What we can do is we look at an address which is a multiple of 4, which is 8. So we need to put a union right here and occupy 4 bytes. This is union. And in between, we just use this space as blank. And by doing so, we are having, you can see 12 bytes. 12 bytes for the S1 struct. Is there any question why we have 12 bytes? Okay, so most of you give the right answers about the 12 bytes. Now I will give you extra 2 minutes. You can look at the second struct. What should be the size of it? Okay, let's do it together. For this one, the starting is also the integer a, and then char b. Now we will look at the struct part. For the struct, the first one is integer, which is 4 bytes. The second one is 1 byte char. We need to accommodate this integer a to make sure it starts with a multiple of 4. So we cannot start right here, cannot start right here, either 7. We need to start at 8. So from 8, we need 4 places to denote a. And after it, we should have char b right here. Okay, so here comes the issue. If we write down a struct 1 array, what would happen? This is the problem we talked about before. If we have the array, then next, starting from 13, we need to put down the next struct's integer a. And the integer a should start with multiple of 4. So 13 is not a place to start. 14 is not, 15 is not, 16 should be the place to start. So we need an extra 3 empty spaces after the inner struct to make sure if we create an array like that, the second struct also satisfying the data alignment. So we need to put down over here as well. So in total, this is 16 bytes. That's the answer. For the second struct, it's 16 bytes. Okay. Is there any questions? Okay, I will write a C program to check our results and also show you what is homework 2 about, and specifically I will talk about function 4. Let's look at my terminal. Now I'm trying to open my terminal. It's right here. Now let's write down a test program. And in the main function, we would put down that struct. First one is integer a, second one is char b, third one is struct again. Instead of it, integer a, and then char b, Here's now we can print out the size of S1 is you can see here the size of S1 is 16. So that means this struct, if we print out the size of it, is 16. Previously, if you don't know the data alignment, you may wonder why the size of struct is 16. Here, right now, you know the 16 is because when we start some variables, we have requirements about what is the address to start the variable, and then we need to insert some blank space in between, so make the space to be 16. And also we can quickly check if we make that to be union. That is union. And it will be 12. Okay. Now let's look at our homework. We talk about the homework. You use the GDB, who am I, to look at the program. Let's look at the first function. Here is the first function. You may notice that at the beginning, we just push RBP, RBX, things like that. And the noticeable part is moving something into EDI and it makes the function call. This function is called a puts. We may make a break over here and let's see what is happening. So you can just type B means break. And then you run the program. So you can see we stop at a function, func1, and right before the function call. We wonder what is 400,830. It seems like an address, right? Now let's check it. We can either use XX or XS, depends on how you want to interpret the space. And now let's look at XS. It is interpreting the space as a string. It is executing function 1. And if we look back at the whoami.c and look at a function 1, you can see the function 1 is having printf message executing func1, right? So it seems like we put this string into our memory, and the location of it is 400,830. This is the address holding that string, and we move this pointer, chart pointer, to EDI. Again, EDI is the register carrying the first parameter. So we give the pointer to the function, and this function called puts. That should be the library function call, something related with printf. And if you look at a call queue, 400,520 is a place for that function. Maybe we can disassemble puts. Oh no, GDB, where am I? This is puts. No. Okay, here's the puts. So you can see here, the puts is 400,520. There's a 400,520. This is the puts function. It seems like we jump to another location. This is the puts at got.plt. Seems like this is a function. Library function. This function wants to print out the executing function 1 message. And after this function call, you can see we have LEA, IMUL. So apparently function 1 is doing arithmetic. It is trying to look at what is arithmetic. And one thing we need to point out is EDI. EDI is carrying the first parameter. ESI is carrying out the second parameter. If you look at the whoami.c, here the function 1 have 2 parameters, A and B. EDI is denoting A, EDX is denoting B. Here, that's one part we need to pay attention to. Where am I? This is from corner. So here you can also see the EAX. It seems like EAX is holding the calculation. Again, the EAX is a register for returning a value. So that's what it means. We do some calculations and put the values in the EAX for return. Okay, this is function 1. And we can look at other functions as well. Func 2. For function 2, you start, the beginning looks like the same. We still doing the printf function, and then we do a test. We have less than equal to. There's a shift greater than or equal to. It looks like we are having some less than equal to. We have some branches in this example because we jump forward. 4007113, there's a 713. We jump forward, so it's probably a branching. So the way we figure out this is we look at what is the conditions for branching, and under each, what do we have done. This is function 2. We also can do function 3. If you look at a function 3, it's due to a less than equal. This is 6e6. There is a 6e6. Compare. Yeah, it still look like the branching structure. Now let's look at function 4. So far, do you have any questions? Okay, Daniel, you can when I describe the function 4, maybe you can put down some of our questions. Yeah, feel free to attend the office hours. That could be very helpful. For the function 4, at the beginning, it's still the same kind of thing. Print out executing function 4, right? And now we're calling a function called IO getC plt. And we make this function call. We want to, okay, let's just do a investigation over here. We want to make a breakpoint at this place. And then we run the program, give a 10, get a C. If you, let's just give 1. Okay. Let's see what would happen. Now we stop right here. we are about to execute call Q, the get C function. We want to step over, so we will next I CS func 4. Now we just step over the get C, and then sounds like that is getting a char from the standard input. That's where I give 1. Let's see whether I receive 1. One thing is, where's 1 is placed? We talk about we make function call, and the place to return 1 is the place to return value is RAX or EAX. Now let's look at EAX. Print EAX is 49. What does it mean? Now let's look at the ask2 tables. I will get an ask2 table. I will share my browser. Ask2 table. For this ask2 table, let's look at 49. 49, where's 49? 49 is right here. And if you look at the character, it's 1. So 49 is ask2 code for character 1. So that's to tell us, go back. That just tell us the EAX right now is having the character 1. I just give the input. So in this way, we figure out EAX. This carries the input you just gave, the character. You type it, and then you would that latter character would appear in EAX. And it seems like we are doing some calculation over EAX, and if we satisfy some conditions, we would set AL to be 1. Otherwise, we would set AL to be 0. So it seems like we either set the return value to be 1 or 0, depends on whether the character satisfy a certain characteristics. Okay, that's a function 4. You need so the question is how we make the return to be 1. So we need to find a proper characters that passes the condition check and make AL to be 1. So this is function 4. Okay. Feel free, you put down your answers in chat window. I can deal with it right away. One question, Jesse, do you still plan on extending the homework assignment? I see many of you hope an extension. Okay, I can do an extension. How many extra days do you need? You can put down some days in the chat window. I can consider how many days I want to extend. Second question from Daniel, what is the logical end of and the EAX2? Okay, for that part, I would say A and D, this is a bitwise AND. This is a bitwise AND. It's not a logical AND. So it will have the bitwise, let me see, bitwise 8 bytes, no, 8 bits, and try to do bitwise AND operation over EAX. In the comments from Nick, it is comparing to the return of get C. Yeah, that's right. And another helpful way is to look at get C. Let me show you get C. Here's my browser again. If you want to look at get C, sorry, let me look at it. Get C. So here's a get C. Return value. The function returns the character rates as the unsigned char cast to integer or end of at the end of file. And you can look at the example. You can get C from standard input, and then the return value is given to C, the character C, and then we print out that. So it seems like the get C, we have one return value, and the return value is in the EAX, and yeah, that is get C. We just get one letter, one character from the standard input. That is what the function is doing. Let me look at what is deadline originally. We have the homework 2. Deadline is 24. Okay, let me see my calendar. So I see many of you like the idea Thursday at midnight, so we can attend 2 different office hour sessions. Okay. So I think that's a good idea. How about let's see, we make the submission Friday night, October 29. Is that sounds a good time?
I think that would be great.
Okay, sure. And let's make that. Let's make the submission October 29, midnight. Okay, so I updated the deadline, October 29. you can always come back, find a deadline from the Piazza. I added the new deadline in the thread. Okay, no problem. Let's see. Do you have other questions? A question from Daniel. Just to make sure it is in the ask2 table. So you can look at an ask2 table. We can have many different characters. Most of the characters we can input. Some of them maybe there's no way we can directly input the character, but most of the characters we can put in. And we need the form satisfying certain conditions. And as long as you find the ask2 codes, which is satisfying the condition, and then convert it back to the character, and then when the program asks for your input, you just put down the character, and then that should work as a result. Daniel, that's another good comment. Some days we would do that 2D arrays. This homework is trying to do a reverse engineering. Yeah, feel free to write down C programs. You don't have to make the C program exactly like generate the exact assembly code. We don't need that. As long as you put down the necessary codes, which make sense, that's good enough. It's pretty hard. You put down exact C program and see the exact same assembly. That's very hard and unnecessary. As long as you put down meaningful codes there describing in a good way, I think that's already good enough. Another question from Amber. Can you explain what a test RDI do? Okay, so the test RDI part is trying to see whether RDI is 0 or not. You can imagine. Oh, by the way, test is the same as the end, bitwise end, except we don't store the final results. If you do a test with the same registers, you can imagine if RDI is non-zero and the same two numbers end together, then it will still be a non-zero number. If RDI is 0, then the results will be 0. So when we do such a test, we are simply testing whether RDI is equal to 0 or not. And another question from Daniel, what is the setEAL and move VBL doing? Let's look back at the source code. Here we go.
It's right there. It's 34 and 37.
Oh yeah, thanks for reminding me. Okay, there we go. SetE. SetE is conditional set. if the condition we check is equal, E is equal, right? And then in the front, we see there's a compare. That means if the compare generate anything equal, we would set AL to be 1. Otherwise, we would set AL to be 0. That's a conditional set. And AL, again, AL is 8 bits. It's a lower 8 bits of REX. And this move VBL, this is special move instruction. You can look at the first one, the AL is 8 bits. The second EAX is 32 bits. That is where the B and L come from. The B is for 8 bits, L is for 32 bits. We are moving from a smaller place to a larger place. You can imagine there's a lot of empty space left. What do we do with the empty space? Do we fill the empty space with 0 or other digits? That's up in the air. So this move ZBL, if I remember correctly, that is filling the place with zeros. So you can check the textbook. There's part talking about move ZBL, what they do, and that is set E and move ZBL. Is that clear, Daniel?
I think so. I still don't exactly know what the C function would look like.
Yeah, you can make a guess.
Would we be able to do, like, not the exact ones for the homework, but write some other C functions that are similar, and you can show us exactly how you would break down each step?
Oh, okay, I see what you mean. Yeah, that's definitely possible. Let me think about it. So how about this? How about actually you can write some C programs and compile it and see what is the assembly look like. So for me, if I create something very similar, the function very similar, I just think it's too close to the answer key. If I was maybe my suggestion would be understand the assembly, what assembly is trying to do. You can give the assembly some inputs, like what I did. I give character 1, and then you track the program, what is the program is trying to do, and analyze this, what the program is trying to do, then write a C program to do the same thing, and that should finish the job. How do you think, Daniel?
Yeah, I'll give it a try.
You can also write it yourself a program. Let me quickly show how to do that. Oh, yeah. Actually, I need a. Choose work. Yeah, here is a way you can compile it. GCC apparently A.C is other key. Anyway, I will just share it here. This is the way I would compile a program. Let's just write down a C program test.c. Right? If you want to look at what the program looks like, insert a equals to 10. If a equals to 0, then do something, printf, maybe. Printf other messages. So you can use gcc-wa-o big O1, that's controlled optimization level to be 1. If you do that, you will see a.out. You can look at gdb a.out. This as main function. Here is the main function. Printf, yeah, it is doing the same kind of thing. So again, you don't have to put the exact C program, generate exact assembly. That is unnecessary. Let me see other questions. Follow up from Amber. Why do we do tests on same registers, RDI and RDI, when we know it will be the same value? The reason is to set up the conditional codes. If the conditional, if you have this, let's see, JE. Let's see, the following instruction is JE. We want to test whether the condition is equal. And then if you do test RDI and RDI, if RDI is non-zero, then we won't jump, because non-zero would interpret it as not equal. So we won't jump. But if RDI is 0 and it will be interpreted as equal, then JE would jump. So it's just a way to test. If RDI is 0, then we make a jump, or RDI is not 0, we don't make a jump. It's just a way to, just the assembly's way to see this kind of logic. Okay, Daniel, that's great catch. In the function I just created, I make a equals to 10, but nowhere move 10 into the register. Why this? That's a really good question. Here is the reason. It controls the optimization level. If you look at my script, let me look back. We have two messages, gdb a.out. It's the optimization level. So if we read the program, we move this guy into EDI and move 0 to EAX in the call queue. Okay, I know why this. So the program, because we set A to be 10, so we know that this program would just print out other messages. We won't print off hello. So the branch is predetermined because we already know A equals to 10. And for the compiler, it just analyze such a phenomenon, and it just make job easier. It won't have branching and testing A again, because it already figured out A is equal to 10, and which is the printf other messages. So it won't do the branching, it's just give you the printf directly. This is optimization from the compiler. Maybe you can even change to 2. I don't know what would happen. This is may to give you a slightly 2 doesn't happen. Maybe open it to 0. Okay. If we put the optimization level to be 0, you can see assembly look like this. We move 10. No. Oh yeah, here. We move 10 to RVP minus 4. So that place we see the move 10 to the place. Because this optimization is 0, our compiler did nothing to optimize the program, and the program just looked like this. Previously, I optimized with level 1. In such a case, we just make things more straightforward. That's the reason. That's the optimization level. That's what I mean. Please don't expect yourself to write the same C program, generate the same assembly code. Yeah, it depends on the optimization levels, compiler versions, many factors, whether you have write out the exact same order in the C program. So that's quite unnecessary. You just read the function and figure out what it's doing, and then write your C program directly. Let me read the chat window. Okay, let me try. Let's accept the letter. We can put down get C. I believe that is get char. That's what I remember. I put it down. Okay, that's right. So right now we want to accept input. We put down get char, and we want to test whether A equals to 1. Okay, let's look at this. Let's run the program at first. It asks for an input. If we give T, and it prints out other messages. If we give 1, it prints out hello 1. And if we look at GDB and this AS main function, this is what the main function look like. So here we still call a getC, IO getC. I think that's the case. I use getChar in the homework too, so it's translated as getC. We want to make a compare with 3.1. This is character one, and the AL should be carrying the character I just input. We make the comparison. If not equal, we jump to some places. If otherwise, we would print off different messages. Okay, so this program may be more close to the homework. Okay, so maybe very close to the homework, and you can make a try. And also feel free to write down the C programs and try to see what is the assembly it generates. Then that could be helpful as well. Okay, great. I'm glad to hear that this example is helpful. And yeah, I will try to adopt this in my next semester class as well. Let me clarify I don't miss any questions in the chat window. Okay, great. Okay. This is homework too. Feel free to attend at my office hours. And I can help you as well. Homework to GDB. What else? Okay, we will talk a little bit about buffer overflow attack. We don't have quite much time left, but let me touch the idea. Okay, we still use this terminal as an example. Let's look at the okay. There's one example I put down here. So right now we are talking about buffer overflow attack, and you can see here for this function we have the char buff 8. We create a buffer of 8 bytes, and then we get something from the get from the standard input, and this would place place the stuff in the buffer, and then puts this function will print out the things we're gonna do. And let's try to run this program. GCC, I just compile it, and then I just print out the stuff. Let's see, we want to do a hello, and you can see here I input hello and print out hello. Let's go back to the buffer program, and you can see here the gets buffer. This one gets the hello I just input, and then put that into the buff. And then I look at the puts function, just get the what I say, get the print out the buffer. We can also try this from GDB. Data out, echo. So here's the program we'll look at. So right now, there is a gets. We make a function call to gets a buffer. And you can see here, for the gets, we need to provide the buffer's address. That address should be in RDI. RDI always receives the first parameter, so RDI should receive the buffer's address. And you can see RAX have it. And if we follow the trend, if we look at RAX, we're having LEA 10, RBP minus 10 to move the address into RAX. So we can make a guess our buffer is starting from this place. Let's just look at it. Okay, I'll make a breakpoint right here. Make sure I guess the character. Now I run the program. Let's put down hello. This is echo. You can see I stop at this place. And my suspect is probably RBP minus 10, which is 16, should have something, right? Should be the buffer. So I use RBP minus 16, and I check the memory address of it. And you can see here, the memory address is E190, something like this. And from this address, we find hello. So we find the buffer, and we find hello is inside. And the buffer size is 8 bytes. Okay, no questions, right? This is quite a standard program. And now let's look at this issue. Suppose right now you're running a server, and the input is given by the internet users. Google is example. You put down the search query, and you send that to Google, and Google have a function to receive your query, and then do things accordingly. In a sense, it's the same kind of process. We want it right now. Suppose you are the Google, you are running this program, receiving the query, and now we tell the user our buffer is 8 bytes. Please don't give more than 8 bytes. How about we give more than 8 bytes? What would happen? So we can put down hello, and the hello, we put down 10 bytes. Something weird may be happening. If we put down 10 bytes, and we move these 10 bytes to the buffer, the buffer is not big enough, and then we could overflow the buffer. And then our program could run into uncharted territory. We don't know what would happen. So it seems like it prints out 10 characters. Isn't our buffer is just 8 bytes, right? Something starts to be weird. Let's just try more. Hello, hello, hello. Okay, 15 characters can still work. What's going on, right? Let's give more. Well, you can see here, we have the segmentation fault. This is a buffer overflow. And we would mention that this buffer overflow can do more than just causing errors. We can specify the inputs in a way that we can control which function in C to be executed. This is quite possible. If we prepare the inputs properly, we could execute any C functions in this program. Could you guess why this could happen? Let's see. Now, if we create a new function, func1, func2, I would say from the buffer overflow, we could execute, even though in the main function, we didn't call this func1, 2, 3, 4, but we can do it using buffer overflow tag. Could you make a guess why we could execute random functions in C? Okay, so I will, since we just have 4 minutes left, I will give you the hints and we will talk more in next class. Why we can execute random functions in C? Yes, Victor, that's good comments. We can execute function 1, 2, 3, 4, any functions in program, even though the main function doesn't call it. The way we can make it happen is to overwrite the return address. Do you remember we have the return address? When we make the function call, we have the return address, and then when function finish its job, it will look at the return address and return to the places, right? For the buffer overflow tag, when we overflow the buffer, we are just modifying the call stack. And there's a chance we overflow the return address part. And we can specify return address at our wish. And we can make the return address to be func1's address. Then after function call return, we would return to func1. Or we could put a return address to be the address of func2, so that when function return, we go to func2. Sounds a fancy idea, right? And actually, it can happen. This is very classic programming attacks called a buffer overflow attack. And we will talk more in our next class. So let me do a quick summary over today's content. So today, we talk about the nested array. We did an exercise that is trying to find geolocate one item in the nested array. So we break down to two parts. The first part in our example is trying to find B3 at first. We find a subarray. And then in this subarray, we further do the offset to look at the index bytes 6. We break down the job into two parts. And also we talk about struct. Struct, we use the space to in a continuous way to store each item. And for the union, the difference from union is it just opens one space and it interprets this space to be different types. And the union could be helpful in some data structures. If we have heterogeneous nodes, some of them use pointers, some of them use data, and then we can make that a union to save a lot of space. And also we talk about data alignment. Data alignment is when we have an object or variable of k bytes, for example, 4 bytes, we must make the starting address to be multiple of k or 4. Because we have such a requirements, sometimes we need to insert some blank space so that make every variable in the memory satisfy the data alignment requirement. Here we give the example, we not only need to make sure the current structure satisfies data alignment, but if we start with array of this structure, we need to make sure the second, the third structure also satisfy such feature. Also, at the end, we talk about buffer overflow attack, and we will talk more in our next class. Okay, that will be today's contents. Thanks for attending. And if you haven't sent me the emails, including your pop quiz, please do so. And that's it. Have a great weekend. Thank you.
Thank you. Have a good weekend.
Yeah, you too.
Thank you for explaining the homework so much. It really did help a lot.
Okay, I'm glad to hear. Yeah, feel free if you have other questions, attend my office hours.
I was looking at it. Is it Tuesday and Thursday 2 to 3 or just Thursday 2 to 3?
Tuesday and Thursday 2 to 3.
Okay, thank you so much. I will be there.
Yeah, no problem. See you later.